All right, there we go. Hello and welcome to a little bit more of a lesson on nets and patterns, and more so to do with scale diagrams. So I'm just getting the door closed here. So hopefully some of the work we do with scale diagrams using ratios is review from grade 9 and previous courses. But if not, I'll do a really thorough job to show you how you can work with ratios easily. So this question was in the previous lesson. We're going to go through it in detail to do with the scales this time. And so this, the link back to the previous materials, it's a pattern, right? So you got like these separate pieces, separate parts, let's say, rather than a net where they'd be attached. So if we're looking at cutting out pieces of wood for this model, then you'd have to have, it doesn't say whether there's a floor, actually it says it does not have a floor, so we don't have to worry about that. I was just looking at the floor on it. So we're going to have a 4x6 rectangle on both sides, so that one times 2. So let's draw a 4x6 rectangle. I'm going to not draw it to scale on my lesson here, but I'll show how to do the calculations for you to do it in your work, okay? So if we're looking at a scale, it doesn't say what scale to use here, but the textbook version of the solution did a scale of 1 inch. So scale, and we have the object and the diagram. I think they did it, scale of 1 to 2. So the scale, let's go object to diagram, and just trying to decide which one was the one to be the bigger one, that's all. But diagram to object. And what I'm showing you here is how I'm really recommending that you carry this out, where you show your ratio. And so if we had the diagram is a 1 and the object was a 2, they did it as like 1 inch to 2 inches, I think it was, or 2 feet actually, sorry. The diagram's feet, right? The object, sorry, this is call this the object. So up here, this is the object. And then the diagram we're going to do is the pattern. And anyway, so it's a 1 inch to 2 feet. So 1 inch on the diagram represents 2 feet in real life or in the object. So if we had it set up where we had a rectangle that was, I can do a better job than that actually. Why don't I grab my rectangle tool here and make it twice as wide as it is long about, but obviously if you're doing a true scale diagram, you'd be measuring. What I want to show here is just the math, the simple way of using ratios to get what the sides would be drawn as. So for the 6 feet one, right, we're going to actually draw it as a certain number of inches, right? So the 6 feet number goes in under the object's measurement heading, think of it as, and then we just need to figure out what the corresponding number of inches is. Right? Some ratios are harder to work with than others. This one's pretty simple. You could probably tell it's 3 easily just looking at it. But what I want to show you is in harder cases of ratios, you're looking for what you would multiply by, and you multiply by the exact same thing as what you multiplied by on the other side of the ratio. Or in this case, the top of the ratio instead of the bottom. You can actually do the same kind of calculations on the side as well, and I'll show that as well, if I remember. Sometimes I forget when I say that. Sorry about that. Anyway, so when you're looking at what multiple it is, I like to describe it as the second number divided by the first number is your multiple. And the second number is always the one you end up at, and the first number is the one you started at. So it doesn't matter the actual direction, forwards or backwards, up or down. Just think of the arrow representing you end up at the second one. And the reason you do that is just because that's how changes always work on things, right? If your bank account changes by a certain amount, maybe you had 80 in there and now there's 100. The second number, the 100, take away the first one would be the difference, or in this case, divided by 80 would be the multiple. How much, what times amount of money you have in there, right? So if I did easier numbers, like 50 becomes 100, 100 divided by 50, you'd be able to tell that your money was doubled. So in this case here, that second divided by first is obviously just a 1 divided by a 2. So in other words, we're multiplying by 1 divided by 2, which is just the same thing as dividing by 2. Okay, so you could put in there, i.e. divide by 2, but it should just be fairly obvious, right? So when you do that, you do the 6 times the 1/2, and you get your 3 inches as a result. Okay, I feel like I should probably do that in red even just to show it's a calculation we did. But so 6 feet is the representation in real life, but we actually make it be 3 inches. Right, so that side would be 3 inches, and then doing the same kind of work. Let me move this over so I have room to show another one of these. So another diagram to object ratio. And again, if the ratios are trickier, like a 7:3 ratio or something like that, it's going to be harder to just guess the numbers, right? So it's easier to have in that kind of case, it's easier if you have a systematic process that will work for you. So that's how I'm showing this very systematically. There we go. So we have the 4 feet that we want to figure out how many inches that's going to be. And I wouldn't need you to go ahead and show the top version in this case, but it's just going to be that times 1/2 again, right? So the 4 times the 1/2 would give 2 inches. And so you'd be able to just label this as 2 inches down here, right? Which of course is the 4 feet. So 4 feet, i.e. 2 inches. Okay, so I don't know how you want to do that for showing it, but basically I want the red to be the actual sides. So if you were doing this, you'd have 2 of those, right? So you just basically have another one of those that you would draw if you're drawing and cutting out pieces of plywood and so on. Obviously, you need 2 of them. Okay, so just show 2 of those. Okay, so the scale work is the main thing I'm trying to accomplish, to show systematically how to communicate that kind of thing and really how to extend that skill to harder cases, right? When I mentioned what if the ratio was like 7:3, it'd be weirder, right? So if it was like a 3:7 ratio, when you're multiplied across that way, you'd be able to say, oh, well, you're just multiplying by 3/7, right? So whatever the number was here, if it was an 11 down here, you just multiply by 3/7, right? So even if it's ugly ratios, you'd be able to work with them. I'll just erase that. So in the printout, you don't see that 3/7 and wonder what the heck it was about to do with this question. So we've got that. Let's look at the other sides as well while we're on this page. So the top roof panels, they have it listed as 2.5 feet. So it's going to say like 2.5 feet. And then of course the 6 is the length still, right? So 6 feet and 2.5 feet. So we need a 6 feet by 2.5 feet representation. So let's do something like that. Put rectangles on here again. We need 2 of those again. So 6 by 2.5, certainly narrower. So let's get something that represents it like that. You would just measure though. I'm just showing the idea. So again, our scale is the diagram. So diagram to, what did I say there? It's a diagram to object. So in the object, we said it was 6 feet and 2.5 feet, right? So we need to do another 6 feet, which is the same as before. So let's just tackle the 2.5. So 2.5 feet. And I should put the scale in there first, like I did last time. So it's a 1 to 2 still. 1 inch to 2 feet still. And so now we have a 2.5 feet that we're trying to figure out what the corresponding number of inches is, right? So this is the same idea as before. You can just say, oh, well, multiply by the second divided by the first, right? Multiply by 1/2. So when you do 1/2 of 2.5, you just get 1 1/4, or you can just certainly run the numbers, right? So you just be like 2.5 times the 0.5, or I could have done divide by 2. Okay, so you get your 1.25. So I'm getting a 1.25 inches. So this would be listed as 1.25 inches there. which certainly represents the 2 feet, 2.5 feet, right? That's supposed to say 1.25 there. My smartboard's still on March break too. Inches. And the 6 was still just that same as before, right? The 6 feet was still just 3 inches. So I'm not going to show that work because it's the same. So this would be 3 inches. And so if you're cutting out pieces of cardboard to represent this thing, it would be 3 inches by 1.25, 1.25 inches, right? So you'd have those 2 pieces and so on and so on. Okay, so the other pieces, we had to have this shape here, right? So this end shape, this cutout out of it or whatever. So let's take that thing over here. And what I might do for this one is just show the calculations that led to the textbook page, because they don't do a good job showing where it came from. But so they're listing this as 2 inches across. Well, where did that come from? Well, that came from the scale that we were using was diagram 2. I'm in trouble thinking this for some reason. Object. I just use that word. I must not normally use it. Diagram to object. Still a 1 to 2, right? 1 inch to 2 feet. And in the object, we're talking about the object itself, it's supposed to be 4 feet. And so the same calculations before, really. It's not always going to be repeated numbers, so it's still good to just sort of go for it, right? But you have your 4 feet, and then you'd say, oh, well, we multiply them by 1/2. And so multiply by 1/2 gives you the 2 inches. So you can see that's where that 2 inches would have come from. And every kind of calculation can be done that way, right? Just start with your ratio, put in, main thing is you have your headings for your ratio, and you have the known numbers in your ratio that are, diagram to object, 1 inch to 2 feet. Once you establish a ratio, then you put the one number that you know, and you find the number that you're looking for. Okay, always just with a common multiple, you'd call it, right? Whatever the multiple is. So I mentioned that I would show the vertical version of this, so I'll come back to that here. If you wanted to know, again, you still wanted to know this number here, right? So the sideways version I'll do in black here. If I wanted to know what I'm multiplying by to get the number that I want, I'd look over here and see, oh, my second divided by my first, my 6 divided by my 2. That's what I'm multiplying by. So I'm multiplying by 6/2, which is the same as multiplying by 3. So you can tell, like, oh yeah, I'm going to multiply by 3, which of course gives 3. 1 times 3 gives 3. Okay, so if you're working vertically with your ratio or horizontally, that's just a nice systematic way to work with ratios. Right? In the new version of this sheet, it's questions 1 and 2 sort of over again. I changed the numbers to make them better for working with scales, and it says to show it on graph paper, which is optional. It's going to make it easier here because you don't have to measure as much, and everything will be. It'll be easier for me to know if you did it right too, right? Because pictures, I can't really measure them. So in this case here, wants a triangular prism and a net made of a triangular prism, and you want the scale to be 5:1. So the triangular prism, the object itself, I'll just jot it down a little bit here for you, is has dimensions of 10 and 30, and so this scale is set up as a 5:1, and so the 10 is going to correspond to a number, and you're going to draw it out. Okay, you're going to calculate it, and then you're going to show the drawn version of it. So it has side lengths. The prism has side lengths of 10, 10, and 10. And then it has the length of the prism is 30. Okay, so picture how you would draw that out. Obviously, you're going to have triangles and rectangles and so on for the net. But the lengths are going to be calculated precisely or specifically to what you're going to be showing. Right? And it'll just be squares here. So I guess in my scale here, I should have said 5 meters corresponds to 1 square. Right? 5 meters in the object corresponds to 1 square. Obviously, you're not going to be able to draw a net, that's 10 meters by 30 meters in any given dimension. That's really big. So this one's reducing the size, right? This is a reduction scale. Or let's just say reduce because I ran out of words, or space for the word, I should say. Well, March break is over and my brain is not quite over it yet. Here we go. So the other one here, we have an object of size of 8 and a net of 1. So this is again another reduction. Again, the diagram is pretty hard to draw, 88 centimeters long on a page. So I put in a scale of 8 to 1. So for the 88, for example, you're going to have your 88 centimeters, right? And you're going to have your corresponding number of squares. And so you'll be able to, I'll be expecting a very specific number of squares for each dimension of each section of your nets. Okay, so that is it. The other page for the assignment has you, I want you to show nets for boxes for each of these Toblerone bars. So if you made a box for these little Halloween ones, the dimensions are supposed to be 4 centimeters by 1.5 by 1.7. That's pretty small. And so you'll see here that I'm doing an enlargement here. So this is making it get bigger. So that's one of the ones where you'd like enlarge for clarity or something to show detail. And this one's gigantic, right? 78 centimeters, that's way, way too big. So I want you to choose a scale that would allow you to make the net on this half of that page in a reasonable size. Use up a decent amount of the page, right? But certainly not 78 centimeters or 78 squares. I don't think there'd be enough room for that. All right, so that's what scales are used for sure, to be able to just show details or fit them in the space provided. And yeah, give it a whirl, see how it goes. All right, if you have any questions, as usual, post questions for me to help everybody, okay?